Hey everyone, welcome back to AP Precalc. Today we're going to be going over FRQ 4. Let's get right into it. All right, so today we're going to be doing 3-peat M, our final 3-peat of the year. So pause the video now if you haven't done this because I am about to go over the answers. All right, so for the first one here, we have the function h is given by that rational function there, h of x, and we want to see what could be a possible graph. So here we're really looking for holes, vertical asymptotes, horizontal asymptotes. So taking a look here, I see two linear factors, x plus 1 and x minus 2. This is going to be something at x equals negative 1, and this is going to be something at x equals positive 2. At x equals negative 1, the multiplicity is higher on the top than it is in the denominator, so it would be top-heavy. When something is top-heavy but seen in the denominator, that is going to make it a hole, and so we should see a hole at x equals negative 1. The ones we don't see that at are D and C, so we can eliminate those two right off the bat. We then also will see something at x equals positive 2, and here the degree of that factor, the multiplicity, is higher in the denominator than it is in the numerator. So this is going to be bottom heavy, and that means it's a vertical asymptote. So remember, vertical asymptotes will be bottom heavy, while holes will be top or equally heavy, but seen at least once in the denominator. Because this is bottom heavy, that means that we will have a vertical asymptote at 2, and so unfortunately both of these graphs have that, so that really doesn't help us eliminate anything. Now let's take a look at the end behavior. So if we look at the end behavior, we're looking at standard form, but we have it in factored form. So remember, one trick to get factored form into standard form is to eliminate any lower power terms and only look at the highest power. So this is really 2x squared times x cubed over x times x to the fourth. This is 2x to the fifth over x to the fifth. This is an equally heavy function, right? Because the degree in the numerator and denominator are the same. And so the rules for end behavior are, in this case, it's just going to be a ratio of the leading coefficients. So as you go to the left or to the right forever, your function should approach positive 2. In this case, it does with b, so b should be our correct answer, and we should see a horizontal asymptote at positive 2 as well. Here in A, we do see a horizontal asymptote at 2, but the function doesn't tend towards 2. It actually tends towards negative 2, making A incorrect and making B the correct answer there. There's a lot to unpack in that question, so this is going to be one of the harder questions, I would say, on an AP exam that you could see that applies a lot of concepts all in one. All right, number 2, which of the following is true about this logarithmic function? So here, remember, log functions will be given as log or a times log base b of x, typically, where if a is positive, the function should look like this. It should be increasing. If a is negative, the function is going to be flipped vertically and will be decreasing like so. Here we have an a value of negative 2 that is negative, and so our function should look like this, which means it will always be decreasing but always be concave up, making C the correct answer. This plus 3 actually has no effect. All it does is move it 3 units to the right, so this function would really just look like that, but the shape would remain the same. All right, number 3. Here we have which of the following is equivalent to sine A cosine pi over 7 plus cosine A sine pi over 7. So here I see sine, cosine, cosine, sine. That's the way we add two sines. So here, this is going to be a sum and difference formula. Remembering the formula, I remember sine of A plus or minus B is going to be equal to sine A cosine B plus or minus cosine A sine B. Here, in this case, A is actually just like the angle A in our problem, but B is pi over 7. Because I see a plus in between and I know it's a sine function, you should have a plus on top. So this should be equal to sine of a plus pi over 7, where that is our respective a and b in this case. This is going to correlate with option C, making C the correct answer there. All right, so the final day we're of notes, we're going to cover FRQ number 4. This is a free response problem that is no calculator and will basically ask you to either solve or simplify equations. So it's very analytical, requires a lot of problem solving ability. Right? These equations or expressions could be anything from exponential to trig to logarithmic to inverse trig, a method, all of the good stuff that you have worked with in the past. Right? There's going to be 3 parts. Part A and Part B are going to be 2 questions each. So AI and AII, and then BI and BII. Each are going to be worth 1 point. Part A will typically be easy, Part B will be a little harder, and then Part C will be hard, but this is just one question that's worth 2 points. So in total, a 6-point question here. All right. 2 of these parts, typically A and C or B and C, will ask you to solve an equation, and then either A or B will ask you to simplify equations as well. So let's just jump right into it. So some general strategies for success for this FRQ is one, just knowing your log and exponential properties, right? If we have log 2 of x plus log base 2y, we know you can multiply the insides, right? Log x times y. You should know your exponent properties as well, right? If we have x squared times x cubed, this is going to be x to the power of 2 plus 3, or x to the 5th. You need to know your trig identities, whether that is sine squared plus cosine squared equals 1, secant squared equals 1 plus tangent squared, cosecant squared equals 1 plus cotangent squared. You need to know what's a reciprocal of what. For example, secant is the reciprocal of cosine, not cosecant. Sum and difference formulas, double angle identities, those are all needed to be committed to memory as well. I would say know your unit circle, right? Solving trig equations. So I would be able to graph the unit circle immediately when you get your test on the AP exam. On your semester summative, same thing. Graph the unit circle because you will need to use it to answer a few of these questions. This is very important. A lot of people struggled with this on the Desmos quiz. Know how to convert from exponential to logarithmic form, right? If you have log base 2x equals 3, you should be able to convert this to 2 cubed equals x and know that x is 2 cubed or 8. And then no inverse trig notation, right? Inverse sine is the same thing as arc sine. There's no difference between those there. Right, so these are the log properties. If we add 2 logs, you can multiply the insides. If you subtract 2 logs with the same base, you can divide the insides. And then any number, let's say 5 log base 10, 7. This is the same thing as log base 10, 7 to the 5th power. That is going to be a property that you will need to know. Same thing with exponents, right? A squared times a cubed equals a to the 5th, 2 plus 3. Likewise, a to the 7th over a to the 4th equals a to the power of 7 minus 4, or a cubed. But then if you have a cubed to the power of 10, this is going to be a to the 30th power. You multiply it when you're raising something to another power like that. Trig identities, here are Pythagorean identity. Remember, with this one, you can get the other two, because if you take sine squared plus cosine squared equals 1 and divide everything by sine squared, you're going to get one of the other equations. You'll get 1 plus cotangent squared x equals cosecant squared x. And then same thing, if you divide everything by cosine, you would get tangent squared x plus 1 equals secant squared x. Need to know that tangent is sine over cosine, so cotangent's the reciprocal of that. Secant and cosecant are also reciprocals of sine or of cosine and sine respectively. And then the double angle and sum and difference formulas will not commonly be tested on this section of the AP exam, but will be tested in the multiple choice and could be seen on this section. So definitely fair game for this question. So with these notes, I am just going to run through these examples here and solve them. Pause the video to try them out before you watch me solve them. And then if you need to, feel free to pause the video, maybe put this in slower speed because I will go kind of fast with these, with what I would expect you to already know. All right, example one, we are just going to start by simplifying exponential equations. So rewrite this in the form e to the power of ax plus b. Here, we're going to simplify e to the power of 3 times 2x as e to the power of 6x times e to the power of x plus 3 all over e to the fourth. We can then add these exponents here to get e to the power of 7x plus 3 over e to the fourth, and then subtract 4 to get e to the power of 7x plus 3 minus 4, or e to the power of 7x minus 1. That should be our answer for example 1. Example 2, very similarly, except here we have 3 different bases, right? They will tell you what base we are looking for, so convert everything to that base in an example like this. Here we have 9 to the power of x plus 4 times 81, which I'm going to rewrite with a base of 9 as 9 squared to the power of 4x, over 3, which I am going to rewrite that 3 as 9 to the power of 1/2. This is then 9 to the power of x plus 4 times 9 to the power of 8x over 9 to the power of 1/2. Simplifying this, we get 9 to the power of 9x plus 4 over 9 to the 1/2. And then this is 9 to the power of 9x plus 4 minus 1/2 is 3/2. So plus 3/2 or 7 over 2 is the equivalent fraction. This should be our answer for example number 2. All right, the next type of problem that you could see is one where you solve exponential equations. Here we're going to set h of x equal to each other, so 5 to the power of 2x minus 3 equals 9. And solving this a lot of times, again, will convert from logarithmic to exponential or vice versa. So here I'm going to convert this from exponential form, which remember a to the power of b equals c, and rewrite it in logarithmic form, which is log base a c equals b. So this should be log base 5 of 9 equals 2x minus 3. Then solving this, I'm going to add 3 to both sides to get log base 5 9 plus 3 equals 2x. And then divide both sides by 2 to get log base 5 9 plus 3 over 2 equals x there. And this should be my answer for example number 3. For example number 4, here set them equal to each other. So 9 to the power of, or 9 times e to the power of 4x plus e equals 19e. I'm going to start by just subtracting e from both sides to get 9e to the 4x equals 18e. Divide both sides by 9. E to the 4x equals 2e. Then I'm going to convert this from logarithmic to exponential to logarithmic. So this should be log base e and then c, which is 2e, equals 4x. We can also rewrite this as just ln, so let me do that now. Now, all I'm going to do is divide both sides by 4 to get ln of 2e over 4 equals x, and that should be my answer there. All right, so example number 5 will require us to simplify logarithms. So what we want to do first is condense this into a single log base 10 expression. And so I'm going to take that 2 and that 6 out in front. So any numbers out in front and move them to the exponent. So I'm going to rewrite this as log base 10 and now x squared minus log base 10 x to the power of 6 plus log base 10 7. Once I have this, I'm going to condense those three logs and combine the insides together. So remember, when you have the same base, which you will always have in this question, the logs, we can multiply the insides together, and if it's subtraction, then we will divide the insides. So what that really means is when you set up your fraction, anything with a plus in front, and including the first term, that's kind of an implied plus, will be put multiplied to each other in the numerator. So here we should have an x squared times positive 7. And then because that x to the 6th term has that minus sign right there, that x to the 6th term is going to be moved to the denominator. Once we have this, if we left that as our answer, that would be marked as incorrect. You do need to simplify. So AP will expect that from you. So we are going to rewrite this as log base 10, and then we can cancel out an x squared from the top and the bottom to get 7 over x to the 4th. And this would be the correct answer for example 5. Example 6, the function k is given by log base 7 x minus 2 minus 15 log base 7 x plus 8 plus log base 7 x to the 4th. Here, again, I'm going to move that 15 to the exponent, so I should get log base 7, and now we have x minus 2 on the inside of the parentheses, minus log base 7 x plus 8 to the 15th, plus log base 7 x to the 4th. Here, combining this into one fraction, I'm going to get log base 7, and then x minus 2 will go in the numerator, x plus 8 to the 15th will go in the denominator, and then x to the 4th will also just go in the numerator. Here, this would actually just be our final answer. So I know what you may be thinking, which is it's not fully simplified, right? You could FOIL out the x to the 4th to both the x and the minus 2 term. However, AP will not expect those simplifications. So if you read the rules at the start of the AP exam for question number 4, you'll see what simplifications they will expect you to make. It's all laid out very nice and neat, but for the most part, you will never have to distribute anything to multiple terms, and you will never have to FOIL anything using the binomial theorem. So that x plus 8 to the 15th can just stay like that. You don't have to, FOIL that out, which would be an absolute pain, especially to the power of 15. So this should just be your answer for example 6. Example 7, here we're solving log equations, so it's pretty simple. Set both sides equal to each other and solve. So here we have log base 3, 2x plus 1 equals 4. And now this is the biggest thing that people get confused on, is if you have log a, log a c equals b, where c is whatever is in the inside of the parentheses, this is equivalent to a to the power of b equals c. So I remember a to the power of the other side equals the inside. Now we need to convert from logarithmic to exponential form here. So we are going to do 3 to the power of 4, and then we are going to set that equal to 2x plus 1. 3 to the power of 4 is 81. This would be something that AP would probably expect you to know or to do by hand without a calculator. Then we're going to subtract 1 from both sides and then divide both sides by x to get 40 equals x. And this should be our answer for example 7. All right, example number 8. Here we have two logs, so ln 3 minus ln 2 plus 4x equals 0. When you see two logs on one side, we're always going to use the properties of logs to condense them into one logarithm. So I'm going to use division here and transform this left-hand side into ln 3 over 2 plus 4x equals 0. Once I have this, I'm going to rewrite it from logarithmic form. So remember, log base AC equals B is A to the power of B equals C. This then should be, remember ln is log base E, So e to the power of 0 equals 3 over 2 plus 4x. Anything to the power of 0 is 1. And then I'm going to multiply both sides by the denominator. So 2 plus 4x times 1 is that, equals 3, and then solve. So I'm going to subtract 2. Really just make sure your algebra steps are correct here and you're not making any silly mistakes. So you should get 4x equals 1, divide both sides by 4 to get x equals 1/4 as your final answer for example 8. Example 9 is a little bit more tricky. Here we are going to multiply the insides together. So this should become log base 3, and then we have x minus 2 times x plus 4, and we want to set this equal to 3. Here we need to FOIL this out. So this is something where you FOIL. This should be log base 3, and then x squared plus 4x minus 2x is just plus 2x minus 8 equals 3. Convert this from logarithmic to exponential. So 3 cubed equals x squared plus 2x minus 8. This 3 cubed is 27, so I'm just going to replace that there. Let me erase this, right? Once we have that substitution, then I'm going to subtract both 27 from both sides. And the reason I'm doing that, so x squared plus 2x, and then 8 minus 27 is minus 35, is to be able to factor, right? Because I see a quadratic here. I need to set one side equal to 0. You can't just factor this back into x minus 2, x minus 4. You have to be really careful about that. So here I'm going to factor this into x plus 7 and then x minus 5. That should add to negative 2, 7 minus 5, and then multiply 7 times negative 5 to negative 35. Here you should get the solutions of x equals negative 7 and x equals positive 5. Positive 5, when we plug it into both equations, right? If we plug it into that one I just circled, 5 minus 2 is 3, that's positive. 5 plus 4, 9, that's positive. This is one solution. However, look what happens when we plug negative 7 into the first log, right? We would get log base 3 negative 9, and you can't take the log of a negative number. You also can't take the log of 0 if that comes up. So we actually will toss this out, making x equals 5 our only solution for example 9. So remember, always check for extraneous solutions with log equations there. All right, example number 10. Here, again, set both sides equal to each other, and then we're using inverse trig. So 21 arc cosine of 2x equals 7 pi. Dividing both sides by 7, we have arc cosine 2x equals pi over 3. Now what we're going to do, and this is what tricked a lot of students on the quiz, is we're going to take cosine of both sides. This will cancel out with the arc cosine, and we get 2x equals cosine pi over 3. Once you have that, cosine of pi over 3 from the unit circle is 1/2. And then remember to not mess up your algebra. Here we're multiplying both sides by 1/2 again to cancel out the 1/2 and the 2 to get x equals 1/4. This should be our answer for example number 10. And then remember, because it's inverse trig, I had so many people on the quiz just want to add that, right? Whenever you are dealing with only inverse trig or inverse trig equals inverse trig, you're not going to have those general solutions, so that will never be a part of it. It will just be a single answer for inverse trig. All right, number 11, let's try this one. Here we have inverse tan, so that's another way to write inverse tan, 2x plus 3 equals 4 pi over 3. And then here I'm going to take tangent of both sides to cancel out that inverse tan there. Here, both sides are neutralized on the left side, so we have 2x plus 3 equals tangent of 4 pi over 3. Tangent of 4 pi over 3 is from the unit circle, it's going to be this angle right here, where tangent I know is positive, at a 60-degree reference angle, so that should just be root 3. Solving this, I'm going to subtract 3 from both sides, and then I'm going to divide both sides by 2 to get x equals root 3 minus 3 all over 2. And you can leave your answer like that. That is our correct answer for example 11. All right, 12. Now solving trig equations. Here in parts A and B, I will let you know right now, when you see trig equations, they will have a restricted domain, or they'll be inverse trig. So they'll either have one or a limited number of solutions. The only time you will see general solutions is going to be in part C. So here, we're looking between 0 and 2 pi. So solving this, 3 plus 2 sine x equals 2. I'm going to start by subtracting 3 to get 2 sine x equals negative 1, and then divide both sides by 2 to get sine of x equals negative 1/2. Here on the unit circle, x is equal to negative, or sine of x will be equal to negative 1/2 at 7 pi over 6 and 11 pi over 6. Remember, we're not taking the square root, so there's no plus or minus with this one. All right, number 13. Here we have 5 minus tangent squared x equals 2. And again, solving from 0 to 2 pi. I'm going to start by subtracting 5 from both sides. So minus 5, that will cancel out. 2 minus 5, this is negative 3. And then I'm going to divide both sides by negative 1 to get tangent squared x equals 1. Or, sorry, 3. Once I have that there, I'm going to take the square root of both sides. And so this is also where I add the plus or minus and then square root 3. A lot of people wanted to add plus or minus to equations like example 12, but we didn't take the square root of both sides, so you don't want to just do that unnecessarily, because then you're adding incorrect solutions to the equation. Once we have this, tangent of x should be equal to plus or minus root 3 at any 60-degree reference angle. So that's going to be pi over 3, 2, 4, and 5 pi over 3. So all 4 of those should be our correct angles for example 13, all 4 of those there. All right. Remember, if you are taking the square root of both sides and then you get the plus or minus, you will have the same denominator for the most part. So either the over 3s, over 4s, or over 6s as well, depending on what your equation and answer is there. All right, so for example 14, here we have an inverse trig equation we need to solve. So we have 7 cotangent x equals 7 over root 3, and we're solving from 0 to 2 pi. Here what I'm going to do is divide both sides by 7 by multiplying both sides by 1/7 here. This will cancel out, so we are just left with cotangent x equals, and then the 7's will cancel out, 1 over root 3. Now remember, before I solve this, I'm going to take the reciprocal of both sides, right? If we have x over 3 equals 5 over y, you can make the conclusion that 3 over x equals y over 5, right? By just flipping both sides. Same thing here. So taking the reciprocal of cotangent, that is just tan of x. And then taking the reciprocal of 1 over root 3, that should just be positive root 3. That's what we're solving. So we're solving tan x equals root 3. And then here you should get x equals, and then this is going to be a 60-degree reference angle. So pi over 3 and then 4 pi over 3 would be the two solutions where tangent is equal to positive root 3 between 0 and 2 pi there. All right, number 15. Here we might need to use the A method on some of these. So here we have sine of x minus sine of x times tan x. And then we want to solve for where is this equal to 0. And so this, what we want to see is we want to factor out a greatest common factor. So what can we see in both of these terms here, right? That's the first term, that's the second. And so I see a sine of x. So I'm going to factor that out and kind of leave it on its own. And then the resulting thing that we will be left with is 1 minus tan x. And both of these are equal to 0. Solving this, I should get sine x equals 0. That one's pretty easy. And then setting this equal to 0 and solving, I should get tan x equals 1. Finding the solutions to both of these, right? For sine x equals 0, in between 0 and 2 pi inclusive, I should get x equals 0. If it was on the entire unit circle from 0 to 2 pi, it would be 0, pi, and 2 pi. But here it's just 0. And then for tan x equals 1, I know that's going to be at pi over 4. And so that should be our only solution there, in between 0 and pi over 2. Right, once we have that, those are going to be our two solutions. So x equals 0, comma, pi over 4. Example 16. Here now we are simplifying trig expressions. You will see one of these for sure on your test, so make sure you know how to do them. The first thing you need to know is your Pythagorean identities. So here, remember, sine squared plus cosine squared equals 1. Dividing all terms by sine squared, we get 1 plus cotangent squared equals cosecant squared. Dividing both or all three terms by cosine squared, you get tan squared plus 1 equals secant squared. So let's use that to our advantage. The first one is g is given by this. Rewrite this only involving secant. So here, 1 plus cotangent, I'm going to first separate everything into its own fraction. Like so. Then I'm going to use any Pythagorean identity to convert anything when you see two parts of an equation, switch it with the third side. So here, this is really cosecant squared x over 1 times tangent squared x over 1. Now, tangent squared x over 1, you don't need to replace this with secant squared x minus 1, even though it is equivalent, because then you're just making it more complicated for yourself. You really want to just get it down to a single trig function without that plus or minus 1. Right? Now we rewrite everything in terms of sine or cosine. So this is 1 over sine squared x, and then tangent is sine squared over cosine squared. Here we can cancel those out. We are left with 1 over cosine squared. And then this, in terms of secant, is I know cosine and secant are reciprocals, so this should just be secant squared x. So remember, to know cosine and secant are reciprocals, opposite letters go together. Let's try 17. Here we have tangent times cosine over sine plus sine over cosine. The first thing I'm going to do is I'm going to simplify this. So what is this equal to? Here, I'm going to just replace it with c and s for now, assuming sine and cosine. So to solve this, I'm going to need a common denominator. I see sine in one denominator and cosine in another. So before I add these two fractions, I'm actually going to multiply this left fraction by cosine over cosine, and this right fraction by sine over sine. That way, I'm going to have a common denominator of sine of x times cosine x. And this is just to simplify this first fraction here. So doing so, I should get this to be cosine squared x plus sine squared x. And then both of these are over sine of x cosine x. Sine of x cosine x there. All right. We can now add these to sine squared x plus cosine squared x. We know that is actually 1. So this is 1 times sine of x times cosine x. And remember, that's what this is equal to. So this whole fraction is equal to that. But that is not our answer. And the reason why that's not our answer is because we can't forget about that tangent that we had. So really, this whole thing is going to be tangent, which is sine over cosine, times 1 over sine times cosine. Here we can cancel out a sine squared, and we are left with 1 over cosine squared x. But we want this in terms of sine squared, so remember to replace sine squared and cosine squared. How do you get them in terms of one another? We want to use sine squared x plus cosine squared x equals 1. Use the Pythagorean identities, and then subtract sine squared x from both sides. This then should be equal to 1 over 1 minus sine squared x, and that should be my solution for 17 there. All right, number 18 here, we want to get everything in its own fraction. So we have cotangent over 1 times secant squared over 1 times tangent of x over 1 times 1 over cosecant. The first thing I see is cotangent and tangent will actually cancel each other out because cotangent is another version of 1 over tangent. So you can either cancel them out from that or convert that first part to 1 over tan of x and then cancel them out there. Now we have secant and we have cosecant, so convert them both into sine and cosine. So this should be 1 over, and then the opposite or reciprocal of secant is cosine. So cosine squared x times 1 over cosecant is just sine of x over 1. Here, I'm going to get cosine squared in terms of sine squared, so this should be sine x over 1 minus sine squared x, and that was using that formula that I already used there. So that should be our answer for example number 18. All right, now we're getting into the problems that you will see in part C. This is like a 2-point question, so it's like double points, but there's only one of these in part C where there is like 2 for part A and 2 for part B, you'll see. Here, these are going to be the harder questions, the one with general solutions, the ones that not a lot of people will get correct. So it's important that you're able to do these so that you can get these points on the AP exam. So the first type is going to be one that requires the A method, either with log or exponential. So here, I'm going to start with example 19. And looking at this, I'm going to set both equations equal to each other to start. So I should get log base 3 of x squared minus log base 3 of x. And I want to see where does this equal 30. I'm going to subtract 30 from both sides. And then I'm going to replace log base 3 of x with the letter a. So I should get a squared minus a minus 30 equals 0. So once I have that, let me erase that line there. Then I'm going to factor it. So this should factor into a minus 6, a plus 5. So make sure you factor correctly. I've had students miss this question and do everything else correct just because they were not able to factor. This should then give us solutions of a equals 6 and, a equals negative 5. Now, remember, this is not our final solution. So here we have to sub log base 3x back in for a here. So this should be log base 3x equals 6. Log base 3x equals negative 5. And then once we have that, we're going to convert it from logarithmic form to exponential. So this should be 3 to the power of 6 equals x. You can leave it like that. AP would not expect you to, figure that out by hand. And then here, 3 to the power of negative 5 equals x as well. Both of these would be solutions because remember, 3 to the power of negative 5, they would probably want you to rewrite this as 1 over 3 to the 5th. But remember, that is still a positive number. It's a small number, but it's still a positive number, so you actually won't really have any extraneous solutions with example 19. Let's try example 20. So here, setting them equal to each other, I have 3 to the power of 2x minus 7 times 3 to the power of x. And I want to see, where does this equal negative 12? I'm going to add 12 to both sides. So once I have that, I'm going to use the a method again and replace a with 3 to the power of x. Now notice how it's not 3 to the power of 2x, because I'm going to rewrite this as 3 to the power of x squared. And that's a small but very important algebra manipulation that was seen on last year's AP exam, knowing that any multiplication of exponents can be broken up into that to the power of this. Replacing 3 to the power of x with a, I get a squared minus 7a plus 12 equals 0. And then factoring this, I'm going to get a minus 4, a minus 3 equals 0. And then a equals 4 and 3 as my two solutions. And remember, sub them back in. So I have 3 to the power of x equals 4, and 3 to the power of x equals 3. Here, I'm going to convert this to logarithmic, so this should be log base 3 of 4 equals x. That's going to be my first solution. And then this one right here would be log base 3 of 3 equals x as well. However, you should know, or you can just figure it out from here, but log base 3 of 3 is 1. So they would probably expect you to convert that to x equals 1 as your true final solution there. So both of those would be the correct answer for example 20. All right, 21, using the a method with some trigonometry. So let's try one of these problems now. Here we have 2 sine squared x minus sine of x equals 1. I'm going to subtract 1 from both sides. So remember, you got to get one side equal to 0. Once I have this, I'm going to use the a method where I replace sine of x with the letter a. This then becomes 2a squared, because it's sine of x squared, minus a minus 1 equals 0. I can factor this into 2a and a would be the first term. I should have plus 1 and minus 1. So that would be the combination, because 2 times negative 1 here, that's negative 2. Negative 2 plus 1 is negative 1 to add to negative 1 there. Then I'm going to solve each one. So when you have 2a plus 1 equals 0, and then a minus 1 equals 0, you should get 1 and negative 1/2 as your two solutions. So let me do that now. Here we have a equals negative 1/2 and a equals 1. And then we're subbing sine of x back in for a. So sine of x equals negative 1/2. Sine of x equals 1. Once we have this, we need to solve both equations. So for this one on the left, I know that this is 7 pi over 6 and 11 pi over 6. And then for the one on the right, I know sine of x should be equal to 1 when it is pi over 2. Once I have those two, this is not my final answer. So if I just said this, I would actually only get one of the 2 points. Remember, the next point is going to come from taking all 3 solutions and adding a plus 2 pi k, because the period of sine is 2 pi. You want to add the plus 2 pi k because here we want to find all values in the domain. So technically, any coterminal angle will work, because sine of 7 pi over 6 plus 20 revolutions will still be negative 1/2, right? So this should be our answer, all 3 of those equations with the 2 pi k is our solution for 21 there. All right, now let's try some trig with general solutions and another trig problem. So you could see either one of these. The first one, let's do together. So here we have sine of 3x plus 2 equals 3 over 2. I'm going to start by subtracting 2 from both sides, or subtracting 4 over 2 to get sine of 3x equals negative 1/2. Then I want to ask myself what angles would sine of what angles equals negative 1/2? We just did that. That should be 7 and 11 pi over 6. So I'm going to set up my two solutions, plus 2 pi k plus 2 pi k. Now the tricky thing is we have that 3 out in front, right? It's no longer just x by itself, it's 3x. So how can we kind of solve and work around that? We're going to have to take this equation and then the next one as well, and I'm going to divide both sides by 3 by multiplying both sides of this equation by 1/3. This equation then turns into x, which is what we want, equals 7 pi over 6 times 1/3 is 7 pi over 18. Very important. And then plus 2 pi k over 3. So notice how that 2 pi k is also affected by that. That is very important to note here. For this one, this should be x equals 11 pi over 18 plus 2 pi k over 3, or 2 pi over 3k, and that should be our answer there. There's no negative sign on that, and those two equations will be our two solutions for 22. For 23, setting these equal to each other, we have 2 inverse tan pi x over 3 equals inverse sine of 1. Now with this one, remember, when you have inverse trig equals inverse trig, there will only be one solution. There's no general solutions because inverse trig has restricted domains. All right? Solving this now, we have 2 inverse tan pi x over 3 equals inverse sine of 1. Where is sine equal to 1 in the domain? That is going to be pi over 2. Now that I have that, I want to get rid of that 2, so I'm not multiplying both sides by 2, but instead multiplying both sides by 1/2. Here, then I should get inverse tan pi over 3x equals pi over 4. And then remember from here, I'm going to take tangent of both sides. This then should cancel out on the left side, and I have pi over 3 times x equals tangent of pi over 4, which is just 1. I'm now going to multiply both sides by 3 over pi to get x equals 1 times 3 is 3 over pi, and that is my answer for example number 23. All right, these questions are very important. You will see one of these and on the semester summative, and the one that you will see will vary from version to version. So you need to know all of them. You can't just ask your friend that took the semester summative an hour before, because you could have a completely different version of equal difficulty. All right, so if you have any questions, please come see me during office hours, and I will see you guys later. Thanks.